Hi, welcome to Problem Solving Experts. In previous videos, I have talked about how to define a problem, and in this video, I would like to talk about how to define performance objectives. So basically, what we want to say is what is the problem, where we are at, baseline performance, where we want to be, which are the objectives, and why, which is the benefits or justification of the project, of justification of the improvements. Now, in this video, I would like to talk basically about three things. One, how to define performance objectives using rule of thumb when we are having two-sided specification limits. How to define performance objectives, also rule of thumb, when we are having one-sided specification limits. And third, confidence intervals for both mean and the standard deviation. Well, let's start. Let's talk. Establishing performance objectives when we are having two-sided specification limits. To explain that, I will be using this example. Let me say that my technical primary metric, the one that I want to improve, is sleep time, and I am measuring that one in number of hours slept per night. The lower specification limit, the minimum amount of time that I should sleep, should be 7 hours per night. And the upper specification limit, the maximum that I should sleep, is 9 hours of sleep per night, with a target of 8 hours. My baseline performance, let's say, is this one. I have a mean, I have an average of 7.5 hours of sleep per night, and the standard deviation of 1.5. The ppms, 529,355. That means that 52.9% of the times I'm sleeping less or more than the specification limits, less than 7 hours or more than 9 hours. In fact, 37% of the times I'm sleeping less than 7 hours and 15.8% of the times sleeping more than 9 hours, especially during weekends. My problem is very big because my sigma is smaller than 2. Keep in mind that between 2 and 3 is big, 3 and 4 is medium-sized problem, 4 to 5 is a small problem, and more than 5 sigma is there's not any problem. But if my sigma is smaller than 2, then I have a very big problem. Well, what should be my performance objectives? There are many ways to establish performance objectives, but the 4 most typical ways to establish performance objectives are these ones: benchmark, rule of thumb, requirements, and entitlement. To me, the best method is benchmark, which is compare with the best. By the way, the objectives, they have to be, doesn't matter what method you use, the objective has to have 5 characteristics. And basically you can remember that one with the word SMART. The objective has to be specific. The objective has to be measurable. By the way, if you have a metric, then it is measurable. The objective has to be achievable or attainable. Objective has to be relevant, and also has to be time-bounded or time-frame, which is for when we should obtain that objective. Well, benchmark is meeting all of these requirements, but especially these two. It is relevant because we are comparing with the best, and if our objective is to have at least the same performance than the best, certainly that is a very relevant objective. And by the other hand, if this benchmark has been able to achieve that performance, then why not us? That means that that objective is achievable or attainable. So to me, that is the best method from the technical point of view. Unfortunately, benchmark can be time-consuming or can be very expensive. So, if for any reason you cannot do a benchmark, then my recommendation is that you use the rule of thumb. and that would be the second choice, or the second, my second option. Requirements is basically a requirement from the customer, a requirement from the executive team, from the headquarters, etc. And in another video, I'm going to talk about entitlement. Then basically, entitlement is to eliminate all the lack of attention to the problem, to the process, all the lack of standardization, all the operative discipline issues, to get the best that you can get from the process as it is now. But well, I'm not going to talk about those methods right now. I would like to focus in this video about the rule of thumb. The rule of thumb states this. It states that if our baseline performance is smaller than 3 sigma, we should reduce PPMs or DPMOs by 70%. And if our baseline performance is greater than 3 sigma, then we should reduce PPMs or DPMOs by 90%. These numbers are not coming from any statistical theory or any algorithm or any technical thing, but basically that is experience. During 20 years of experience that I had coaching projects and executing projects around the world, well, I have seen in a big database that I have that when we are starting a process with a performance smaller or equal to 3 sigma, in 95% of the times we are getting an improvement of 70% PPM reduction or greater. In this big database, more than 20 countries, more than 20 years, when we have started a project with a performance, with the performance of the process greater than 3 sigma, in 95% of the times, we have achieved an improvement of 90% or greater. So, well, basically, based on that, just historical data, that's how this rule of thumb has been established. Again, there's not any theory behind, but it's just experience, and that's why I call it rule of thumb. So, for the example that we are having, because our baseline performance is 1.37 sigma, which is smaller than 3 sigma, we should reduce the 70%, the PPMs by 70%. That means that instead of having 529,000, I'm going to have 30% of those defects as my objective. Again, I will be removing 70%, and I'm going to get 30% of this baseline. And basically that performance is $158,806.5. And that should be my objective, because this is 30% of the baseline. Well, we have established the objective in terms of PPMs, but also I have to establish the objectives in terms of mean, in terms of standard deviation, and in terms of sigma. When we are having two-sided specification limits, to establish the mean, the objective mean, is very easy, because the objective mean has to be the center of the specification limits in most of the times. So for this example, the center of 7 and 9 is 8. Then my objective mean has to be 8.0 hours of sleep. And well, basically now what I have to establish is what is the standard deviation that I need in order to have 158,906 ppms having a mean of 8. And well, basically we can do that. And how are we going to do that? Well, we have to take a look to this one. My new performance, the objective that I want is this one. I want to have my normal distribution, I want to have my lower specification limit, which is the 7 hours. I want to have an upper specification limit, which is the 8 hours. I want to have a mean, which also is the target of 9 hours here, and also of 8 hours. And I would like to have a distribution, a normal distribution, let's say, centered here. Basically, what I would like to have is half of these defects above the upper specification limits, because this is centered, and half of these defects below the lower specification limits, which are those limits. Which basically, that means a number like this one is 79403.25, and also 79,403.25, and those should be the ppms objectives that I would like to have on each side of the curve. I would like to have 79,000 ppms in order to get 158,000. So now I can take as a reference any of both limits. In this example, I'm going to take this upper specification limit, and I would like to calculate the Z upper. Well, let me do that. I'm going to make some space here, and let me do that. The Z upper, the definition of Z upper, is equal to upper specification limit minus the mean divided by standard deviation. Remember, in previous videos, I have talked that Z is number of standard deviations that fit between the mean, in this case here we are having the mean objective, and the upper specification limits. How many standard deviations fit here? So we are having the range, upper specification limit minus the mean, and now I have to divide by the standard deviation in order to know how many standard deviations fit there. By the way, I want to have the mean objective, the standard deviation objective, in order to get the Z upper objective. Okay, question, what is the Z objective? I need to know how many standard deviations I have to have in this region in order to get this amount of defects, 79,403 defects. And I can get that from a table, the table for the normal distribution. Keep in mind, remember in a previous video, I have said that the area of the normal distribution, of the Gauss distribution, is very well characterized in terms of number of standard deviations. So all what I have to do is to look for this area, 79 ppms and 400 ppms, to get the Z that allow me to get this area, So well, let's take a look to the table. If we take a look to the table, is 79,403. 79,403. The closest value is 1.41. 1.41. Okay, then from table we are getting that the Z upper objective has to be 1.41 to be able to have 79,400 ppms. That means that the distance that we should have here is 1.41 standard deviations to be able to get this area. From the formula that we are having, Z upper objective is equal to upper specification limits minus mean objective divided by the standard deviation objectives, we are able to calculate what should be the standard deviation objective, because we already have the Z upper objective, we already have the upper specification limit, we already have the mean objective. So basically what we get here is that the standard deviation objective is equal to upper specification limit minus mean objective divided by Z upper objective. Then the standard deviation objective is equal to upper specification limit, 9, minus mean objective, 8, divided by the upper objective, 1.41, which basically this is this distance that we are having here. And from there we are getting the standard deviations. Let's do the calculations. And well, the standard deviation is 0.709 hours of sleep per night. Then our standard deviation objective is 0.709, and that will be the standard deviation. The only missing value that I don't have yet is what should be the sigma. Well, we are going to use the same table that we have used for the normal distribution. And basically, I would like to let you know that there is a very important definition about sigma. Sigma, basically, sigma value, that is for the short term, is equal to the bench plus 1.5. How are we going to get this Z bench? Same table that we have used to get the Z value for 79,000. That's the same table that we are going to use. But in that table, we are going to look for the total area, not one side area. The total area, 158,806 ppms. And we are going to look for what Z value is equivalent to this area. That value that leads to this area of Z is known as Z bench. To that value that we are getting from table, to get this area, we are going to add 1.5, and that will be the sigma value. Well, let's take a look to the table. On the table, you are looking for a ppm value of 158,806.5. And the closest number that we are getting is 158,655, which is a Z value of 1.00. Okay, so then our Z bench, to calculate the sigma value, so we are going to do sigma value is equal to 1.00, which is the Z bench that we have found on the table, that is getting the 158,800 ppms, plus 1.5. Then our sigma objective has to be 1 plus 1.5, 2.5 sigma. Our objective is to increase our sigma performance from a very big problem, 1.37, to a big problem, 2.5 sigma. And that's how we establish performance objectives when we are having two-sided specification limits. Basically what we do is that we set the mean at the center, and we found what the standard deviation is necessary in order to get 30% of the baseline ppms. Now, I would like to talk about calculating performance objectives when we are having one-sided specification limits. Establishing performance objectives when we are having one-sided specification limit. Well, it's the same thing. You can use benchmarking, which is the method that I recommend the most. You can use rule of thumb. You can use requirements, demands from the customer, from the executive team, or you can use entitlement, which is eliminate all the operative discipline issues. I'm going to focus in this video on rule of thumb. Rule of thumb, if your baseline performance is smaller than 3 sigma, reduce PPMs by 70%. If your sigma is greater than 3 sigma, reduce PPMs by 90%. Let's use this example for one-sided specification limits. The technical primary metric, the one that I want to improve, is exercise time, minutes of exercise per week. And I'm having a lower specification limit of 135 minutes per week. That means that the minimum that we should have is 3 sessions of cardiovascular exercise, 45 minutes each session. And greater is better, so there is not an upper specification limit, so the more you exercise, the better. And also, let's say that my baseline performance is this one. Currently, my mean is 140 minutes with a standard deviation of 15 minutes per week. The PPMs, 460,172, which means that 46% of the times I am exercising, 46% of the weeks, I am exercising less than 135 minutes per week. The problem is very big also because sigma is smaller than 2. What should be the performance objectives? Well, we are going to use the same mechanics, but there will be a small twist in terms of calculating mean and the standard deviations. For the calculation of PPMs is exactly the same. My objective is to reduce 460,000 by 70%. That means that my objective should be 30% of the baseline. And that 30% is something like this one. Okay, this is the objective. 138,051. That is the objective in terms of PPMs. Now, how to establish mean and standard deviation? Well, in this case, we don't have a target for the mean because the greater is better. The more we exercise is better. The rule of thumb establishes that when you have one-sided specification limit, you should try to reduce variability to half. And that means that if your standard deviation is 50, then you have to reduce standard deviation to half, which is, in this example, 25 minutes of exercise per week. The reduce variability. We always want to improve control, and improve control means reduce variability. Now the question is, what mean is necessary to get 138,000 ppms having a standard deviation of 25? Well, that's the same thing. In this example, we are going to use Z lower. So the Z lower is equal to Z lower objective is going to be the mean, no, the mean objective minus the standard deviation, no, minus the lower specification limit divided by the standard deviation objective. Okay? I have the mean objective. No, I don't have the mean objective. I have the standard deviation objective. I have the lower specification limit, and I can get the Z lower objective. What is the Z lower objective? Z lower objective. Well, same mechanics that we did before. We need to take a look to the tables of the normal distribution and find the Z value that is leading us to get this area. So let's take a look to the table. Let's look for this area, for these ppms, and let's see what Z value is necessary to get this area. Okay, if you take a look to your table of normal distribution and you look for 138,000, the closest value to 138,000 is 137,857, and that is a Z value of 1.09. Okay, so the objective, 1.09. Objective. The mean objective is equal to lower specification limit plus the lower objective times standard deviation objective. Okay, and you're substituting our formula. So the mean objective, which is the value that we want to get, is equal to lower specification limit, 135 minutes of exercise per week, plus the lower objective, 1.09 number of standard deviations that are necessary to get this area, times the standard deviation objective, which is 25. Then the mean objective is equal to, let's do the calculations. Well, then our mean objective is equal to 162.25 minutes of exercise per week. Then I have to increase my exercise time average from 140 to 162.25, reducing the variability. Also, I have to exercise more time and more consistently reduce variability to 25 minutes standard deviation. And my ppms will be reduced by 70%. Now, what will be the sigma value? Well, we have to do the same mechanics. We have to take a look to the table for this value, and that's going to be the z-bench. Z-bench plus 1.5, that's the sigma value. If you remember, sigma level, sigma value is equal to z-bench plus 1.5. But because one-sided, all the area is only in one side. So we already have obtained this value, and what we got is that the z lower objective is the same than the z bench. Then our sigma value is 1.09 plus 1.5. Then our objective is to have a sigma of 2.59 sigma. And well, that is our objective, 2.59 sigma. And those will be our performance objectives. So right now, baseline, we are having a very big problem, 1.6 sigma, and we want to increase almost 1 sigma to get a big problem, which is between 2 and 3 sigma. And those will be our performance objectives for and also later, this can be a second project, this can be a new baseline, and you can repeat the process and so on. And well, basically that's it in terms of calculating performance objectives when you are having two-sided specification limits and when you are having one-sided specification limits. Now, it doesn't matter what method you are using to establish performance objectives. Your objectives have to be SMART, specific, measurable, attainable, relevant, time-bounded, but also the mean and or the standard deviation has to be outside confidence intervals. Otherwise, your objective is not, the change that you are looking for is not significant from a statistical point of view. Then let's talk about confidence intervals. Well, as I have said, when you have established performance objectives, you have to make sure that the mean and or the standard deviations be outside confidence intervals. And what the confidence intervals are? Well, let me introduce the concept. Usually we are having a population, size n, with a mean and then standard deviation. and we don't know the characteristics or the parameters of the total population. So usually what we do is that we take a sample, and that sample is going to be have with a size, and it's going to have a mean and a standard deviation. By the way, just let me tell you that when we are talking about a population, and when we are talking about sample, usually when you are talking about the mean, we will use for the population a Greek letter, mu, and for the sample we are using, if it's an output, y bar, if it's an input, x bar. And also when you are talking about the standard deviation, we will use the Greek letter sigma for the standard deviation, and we will use S for the sample. Also for size, usually what we use is like capital N and small n. So well, basically when I'm writing Greek letters, I'm talking about population. And when I'm using Latin letters, then I'm talking about a sample. So just that's important to understand, because sometimes I'm going to use Greek letters, sometimes I'm going to use Latin letters. Let me come back to this one. And basically, you take a sample, and guess what? The mean and the standard deviation of the sample are not going to be, is very unlikely to be, exactly the same than the mean and the standard deviation of the population. If it's a representative sample, they are going to be close, but they are not going to be exactly the same values. Well, if I take a new sample, size n, you will get a mean, you will get the standard deviation, and guess what? The mean and the standard deviation of the second sample is going to be also different than the mean and the standard deviation of the population, but also the mean and the standard deviation of the second sample is going to be different than the mean and the standard deviation of the first sample. So you are going to get as many means and as many standard deviations as number of samples you have taken from the same population. Then the question is, what is the mean and the standard deviation of the population? And the answer is, I don't know. We don't know. And in addition, we are never ever going to know exactly what is the mean and the standard deviation. Even if you take a census and you collect the whole data of the whole population, well, also it can be variability because of the measurement system, and then that introduces some uncertainty to the values. But well, anyway, so coming back, what is the mean and the standard deviation of the population? Answer, don't know, and I'm never going to know. But well, we can define an interval of values where it is very likely that the mean of the population be, and an interval of values where the standard deviation of the population be. And to that range that we are going to establish, we are going to call to that one confidence interval. So if I take a sample, maybe the mean, let me say for the mean is going to be here. I take a second sample, the mean is going to be here. A third sample, the mean is going to be here. A fourth sample, the mean is here. A fifth sample is going to be here, etc., etc. So where is the mean of the population? I don't know. But it's very likely that the mean of the population be somewhere between this range. And that, again, as I have said, we call confidence interval. So, by the way, we also have to pick a confidence level. So usually we are going to establish a confidence interval for 95% confidence level. So we are taking a risk of 5%, and we are going to call to that risk alpha. Alpha, which is the alpha risk, is 5%, or also alpha is 0.05. So basically what we are going to say is, if somebody asks you, what is the mean of the population? The answer will be, I don't know. But with 95% confidence level, I can tell you that it is somewhere between this value and this value. So we are going to provide a range, an interval, where the is very likely, 95% confidence level, than the mean of the population be. And we can do the same also for the standard deviation. So, for instance, if my mean is 140 minutes of exercise per week, in the example that I have given, I have to make sure that my objective, 162, be outside, for this example will be above, outside the confidence interval. If 162 is not outside, is inside, well, that's not a significant difference, significant from a statistical point of view. Because all what you have to do is do nothing, just take another sample, take another sample, take another sample, take another, and eventually in one of the samples, without doing any change, you are going to get that mean. Well, if inside confidence interval, but at this point I don't know if this value is outside or inside confidence interval, so I have to calculate the confidence interval for the baseline. Always you have to calculate your confidence interval for the baseline. Okay, so let's do that. How to calculate the confidence interval for the mean of the population? This is mu, a Greek letter. Well, using this formula. How can you calculate the confidence interval for the standard deviation of the population? This is sigma, population, using this formula. Let me explain first how to, let's in fact calculate the confidence interval for the baseline of exercise time per week that we have here. So, well, let's first make sure that we are having all the values that we are asking for. I'm going to erase this part to make some space. So, the mean, I already have my baseline mean, 140. The standard deviation, I already have my baseline standard deviation, which is 50. And sample size, in this example, I said that a sample size is equal to 10. But I have this term, and that term is t-value, the t-value. The value of t is coming from a table. T-student table, T-student table. And this T-table or T-value is coming from a table like this one, T-test. So let me do that one, let me do T, and you can get here alpha divided by 2, comma, 9 minus 1. And that is basically a value of T with alpha, a risk of 0.05 divided by 2, n, which is 10 values, minus 1. Then we have to get t from tables of 0.025 because half of the risk is going to be above the upper confidence interval and half of the risk is going to be below the confidence interval. So we are going to have 2.5% of error and 2.5% of error on each side. So on each tail we are going to have 2.5% of the error, comma 9. This n minus 1 is known as degrees of freedom. The degrees of freedom, df, is equal to n minus 1. In this example, we are having 9 degrees of freedom. I have written part of the T-student table here. And for this T, you can have different alpha divided by 2. We are going to use the column that is in the middle, which is 0.025, that's alpha divided by 2. So this is the column that I will be using. And for that column, the degrees of freedom is 9. Then these are the degrees of freedom to use. This is the alpha to use. And then the value that we are getting there for T is 2.262. So the value of T is that one, is 2.262, and that will be the T test, the t-value. That's coming from tables. When the degrees of freedom become infinite, this will be the z-value for the normal distribution, 1.96, but well, I'm not going to talk about that one right now. So from there, I have all the parameters that I need in order to calculate this confidence interval. And that's what I'm going to do right now. Let me just do this first part, which is t of t times s divided by the square root of n. That is 2.262, value of t, times the standard deviation, which is 50, divided by the square root of number of values. Number of values is 10. Then this term, the value for that term, is going to be equal to, and let's do the calculations. Well, 35.76 is this term. Then is all this term. The confidence interval for the mean, the baseline mean, is equal to the mean, 140, minus 35.76, and that is smaller equal than mu, the mean of the population, smaller equal than 140, plus 35.76. So that is equal to 104.24, smaller equal than mu, smaller equal than 175.76. And that is the confidence interval with 95% confidence level. 95% confidence level. What is the meaning of that? According to my sample, the mean of the sample that I have taken, of the data that I have taken, is 140 minutes of exercise per week. What is the actual mean? What is the mean of the population? The answer is I don't know, and I'm never going to know. But with 95% confidence level, I can tell you that the mean of the population is somewhere between 104.24 and 175.76 minutes of exercise per week. Somewhere inside here is the minutes of exercise per week. Then, for this example, the mean that I'm having, 162.25, is inside confidence interval. So that means that that is not a significant change. So, well, what do we do? One of the options is to propose a more aggressive mean. Well, instead of 162, it has to be a value greater than 175. But there is another option, and that other option is, well, let's collect more data to see. It can happen. It's not a fact that it will happen, but it can be that if I take more data, now the objective can be outside confidence interval. Why am I am saying that? Well, when you are collecting more data, you are having more certainty of where the population is. If you are having a very small sample, you have a lot of uncertainty, but the bigger the sample is, your uncertainty will be decreased, and then the confidence interval is going to narrow down. We can see that effect here on the formula, taking a look to the formula. For instance, you are having a square root of n, square root of n. If you increase this term, all this value is going to be smaller because you are dividing by the square root of sample size. So this term is going to be smaller. And if this term is smaller, you are going to add a smaller term a smaller value to 140 and to add a smaller value to 140. That has the effect of decreasing, making the confidence interval width more narrow, so it's decreasing the width of the confidence interval. But you have a double effect, because if you take a look to the t-table, when you increase the degrees of freedom, keep in mind that degrees of freedom is number of values minus 1. So when you increase the number of the sample size, you increase the number of degrees of freedom, the t-value is going down: 12, 4.3, 3.1, 2.7, 2.5, 1.96. So you are decreasing the value of t. If you decrease the value of t, this value will be smaller, and if this value is smaller, this value also is smaller, so you will be adding a smaller value to 140 and subtracting a smaller value to 140, and you will be narrowing down your confidence interval. So if you increase your sample size, it will be a fact that the confidence interval will be more narrow. You will be increasing, you will be decreasing the width of the confidence interval. But any of the following things can happen. It can happen this. This is my original confidence interval. If you increase your sample size, any of these things can happen. It can happen this. But also, it can happen this. Or also, it can happen this. In every case, the interval is going to be smaller. The interval is going to be smaller. But we don't know where is going to move the mean. I mean, it can happen that centers, or it can happen that goes to the right, or it can happen that goes to the left. It will depend on where the actual mean of the population is. If the mean of the sample was this, but the actual mean of the population is here, then what's going to happen is this one. That is what is going to happen. If my sample is here, the mean of the sample is here, but the actual mean of the population is here, when you collect more data, then this is what's going to happen. So the confidence interval is going to move where the actual mean of the population is. And we don't know where the actual mean of the population is. If it's here, if it's here, or if it's here. So we don't know where the center of the confidence interval is going to move to. Always is going to decrease. It's going to be more narrow. But again, we don't know what's going to happen. So if you have established, give me a second, if you have established that your objective is this one, and you increase your sample size, it can happen this. The same mean of the sample, oh, now it's outside confidence interval, I don't have to change my objective because it's outside confidence interval. But also it can happen this, still to be inside confidence interval. And now that you have a bigger sample size, the mean of the sample is moving from here to here, and then it's going to be inside. So in that case, you have to change the mean for a more aggressive mean, or recalculate using the rule of thumb the objective mean and the objective standard deviation with the new sample that you are having, the bigger sample that you are having. Well, I have talked about the impact of sample size in confidence interval. Now I would like to talk about the effect of changing confidence level into confidence interval. What it is expected is that the greater the confidence level, which means the smaller the risk, then the wider should be the confidence interval. And the expectation is, well, let me share this example. With 99.99% of confidence level, I can state that the age of the persons that are watching this video is between 3 years old, and 103 years old. As you can see, I am very confident that I am right. And the reason of that is because I am providing a very wide confidence interval. Of course, if I reduce the interval, for instance, if I say, well, the age of people watching this video is between 15 years old and 75 years old, well, I'm taking chances to make mistakes. I'm taking some chances, and then the error increases, or the potential, the probability to fail increases. So the wider the confidence level, also the wider the confidence interval. And well, we can see that, we can explain that, taking a look to the formula. If you take a look to the formula of confidence interval for the mean of the population, let's take a look to t-value, t-student value, which is coming from a table. So we can take any degrees of freedom, whatever number you would like to take, and you can see here that the risk is going down, which means that the confidence level is going up. So for instance, here is 90% confidence level, 95% confidence level, 98% confidence level, 99% confidence level, and so on. So the confidence level is increasing to the right. So when we increase the confidence level, you will see that t-value also increases. Take any of the rows for on any degrees of freedom, and whatever you are taking, you will see that t increases. If t-value increases, then this term will increases, which means that to the mean, you will be subtracting a bigger value, and to the mean, you will be adding a bigger value. And the effect of that is to increase the width of the confidence interval. And you are doing that because you are increasing the confidence level, and you are doing that because t-value is increasing. Well, now let's talk about a confidence interval for the standard deviation of the population. And well, basically we have to do the same mechanics, and that's going to happen always the same thing for the standard deviation. Let's take a quick look to the standard deviation. Let's take a look to the confidence interval for the standard deviation. So I'm going to erase here the t-student table, and here I will be calculating the confidence interval for the standard deviation. So one of the terms that I need is the standard deviation of the baseline, which in this case is 15. N, which is the sample size, is very small, is 10. And here I need to get this chi-square value. But by the way, we need to get two values. One chi-square for 1 minus alpha divided by 2, and 1 chi-square for alpha divided by 2. So basically, those values are obtained also from tables. So chi-square table, so you will be using chi-square table. And from there you are going to get that value, and from there you are going to get that value. So you are going to get a chi-square value. Let me use this other color very quickly. Chi-square value for 0.975 and chi-square value for 0.025. And by the way, in those cases, you also are going to get degrees of freedom are going to be 9 for one of the cases. And well, let's take a look to the tables. If we take a look to the table of chi-square, degrees of freedom of 9 and 1 and 0.025, then we are having a value of 2.7. Degrees of freedom of 9 and 97.5. We are having a chi-square of 19.02. Okay, then here we are having the values of tables. For the confidence interval of the standard deviation of the population, let's do the substitution of the values. The standard deviation is 50 times the square root of n minus 1, which is 10 minus 1, divided by chi-square of 1 minus alpha divided by 2. That is 1 minus 0.025, that is 0.975. And that is 0.975, the chi-square was 19.02. Smaller equal than the standard deviation of the population, smaller equal to 50 square root of 10 minus 1 divided by 2.7, which is the chi-square of alpha divided by 2, which is 2.7. Okay, let's do calculations. Well, here we have our confidence interval for the standard deviation, 34.39 to 91.29. What is the standard deviation of the sample? 50, baseline. What is the standard deviation of the population? I don't know. And I'm never going to know where is the standard deviation of the population. But with 95% confidence level, I can tell you that the standard deviation of the population is somewhere between 34.39 and 91.29. My objective standard deviation is 25 because the objective is smaller than 34.39, that is 25. That means that is outside confidence interval. And that means that that's a significant change. So if you cannot or you don't want to collect more data, a bigger sample size, what you can say is that you are not really defining a significant change on the mean. But your main objective is to have a significant change in terms of the standard deviations, which means that I have to exercise more consistently. Some weeks I'm exercising a lot, some weeks I'm not exercising at all, so now I want to be more consistent. Maybe the mean won't change in a significant way, but because of the consistency, I will have an improvement, and that improvement will lead me to 70% ppm's reduction. And well, basically that's it for today's video. Thank you very much.